So today we're going to give some details about the proof of the following theorem. Okay, so first of all, I'm having the Euler equations, which I write in the following form. Okay, and I will consider the Euler equations actually on the full space. So this is going to be on Rn times minus infinity, infinity. What would people call eternal solutions. So I don't have boundary conditions anywhere. And I'm going to consider what people call weak solutions. Okay, and for us, the formal definition of weak solution is that if it's what you would find. So if you know that this thing is equal to 0, you scalar multiply by a function phi, a vector function phi, and you can integrate by parts, and then you get an identity for the integral. And that is going to be, of course, that identity is going to be true for every function that you multiply this guy by. And now the definition in the sense of distribution is that I'm assuming that identity holds, okay? So it means that if I multiply so if let me just think about it, maybe because I'm integrating by parts, maybe maybe this here actually has a right, as a minus. Yes. Okay, I assume that this one is equal to 0 for every test function psi, which is C infinity and compactly supported on Rn, and which is a vector field. And at the same time, okay, so actually, no, written in that way is wrong, sorry. So I should really write it in this way, sorry. It's P divergence of psi. Sorry. Is equal to 0 for every psi which is C infinity and compactly supported, and at the same time, U dot gradient of phi is equal to 0 for every phi which C infinity and compactly supported. Okay, and so this is the definition of weak solution. And to be a weak solution, what do you need? You need to make sense of these objects. So you need the function u to be at least locally in L2 so that you can multiply the components of u with themselves. Okay, so u is locally in L2, and P at this point is just a distribution such that, okay? And the theorem that we are after, sorry? Yes. Where, in here? But it has to be compactly supported. Oh, sorry. This is just. Sorry, here I just forgot, okay? Actually, in principle, even here, I forgot. But I mean, here it's less important. You are perfectly right that here I could actually have done only with the time-independent one, but in here it's important. Okay, yes, this integration is in time and space. In both cases, okay? Even though I wrote only one integral. Okay, so and here is going to be the theorem. And I'm following the proof that La'szlo and I gave, in our paper in 2013. 7, I mean, we really wrote it in 2007. It was published slightly later, I think, in 2008. And the theorem is that, so there exists pairs V and P, which are in L infinity, weak solutions of the Euler equations in time and space. So this is what I will call E. On Rn times minus infinity, infinity. N is at least 2, of course. Which are compactly supported in time and space, and non-trivial, so not identically 0. Okay, in fact, we will prove something stronger. What we will really prove is that for any omega that you give me in time and space, let's say bounded, there exists Vp, which are L infinity weak solution of E on Rn times minus infinity, infinity. So they are compactly supported, but in fact they satisfy much more. So here's what they are going to satisfy. So V is identically equal to 0 outside of omega, actually both of them. So not only they are compactly supported, but they are compactly supported in omega. And then I'm really forcing a much stronger condition on the fact that they are non-trivial. So V, the modulus of V is actually going to be equal to 1 in omega. Okay? So there's this omega. Outside of this omega, the fluid is at complete rest. And this omega is compactly supported in space and time. So you don't see it back in time, so everything is completely equal to 0. Then at a certain point, you see the first slice of omega, for instance, if omega is the ball of radius 1 times the time 0, 1. And in there, the velocity has exactly modulus 1. So I'm not telling you where it is directed, but the speed is exactly modulus 1. And it keeps being that way inside this patch. And then, poof, it disappears. Okay? So, as I said, I will give you some idea of the proof, but you know, the paper is actually relatively simple and self-contained to read. So rather than like insisting on the details of this or that lemma, I will actually try to give you some of the main ideas, okay? And then maybe like, you know, some lemmas I will give you as an exercise, and some other complicated things I will do it on a little bit simpler model, just to get an idea of the proof in a situation in which certain problems are not there, okay? Very well. So the first thing that we will do is we want to rewrite the Euler equations in a form which looks funky. So we rewrite the Euler equations in the following way. So let me add a, okay, so now I realize actually that maybe I want to call the variable V instead of U. Sorry about that. You will see in a moment why. Okay, so then I have V everywhere over here. Okay, and there it is V already. So I want to actually introduce a matrix for this quantity over here. So let me call this matrix U. And write my equation in a form which is completely linear first. So this is just a completely linear equation. Okay. And then it's coupled with, of course, the fact that my U is equal to V tensor T. Okay, but let me do something which is slightly more sophisticated. Let me actually note the following. Let me change the pressure to Q. And instead of putting U over here equal to V tensor V, let me put it equal to to V tensor V minus V squared divided by N times the identity. So that makes this matrix trace-free, okay? That makes this matrix trace-free. But of course, the equation is not true anymore, right? But what is the divergence of modulus of V squared divided by N times the identity? That is the gradient. So if I kind of change variable to the pressure, and I put as new variable for the pressure this guy, okay, then you see that the gradient of this portion, which is coming from the new pressure, is canceling with the divergence of this guy over here, okay? So this is a complete rewriting of the equation. Okay, so let me just therefore kind of stick to this. But notice another interesting thing. So another interesting thing that you can do is you can construct this matrix. And if you put together the time and space variables, okay, you actually realize that this system of equations, so let me call it the linear equation, and let me call this one the algebraic constraint. So the linear equations are actually equivalent to divergence of big U equals 0, okay? Okay, and because I'm actually trying to solve the equation not only with that constraint over there, but I'm also actually asking that the modulus of V is equal to 1, let me actually add that one to the algebraic constraint. So forget about the pressure, because the pressure, I can call it Q, and then I can recover P by simply subtracting modulus of V squared divided by N from Q. So it's really not important, it's not a constraint. I change variables and I don't see it anymore, but the additional constraint that I put over here is modulus of V equal 1. Okay, then your theorem. So the reformulation of your theorem is the following. So what I really want to show is I want to show that there exists a U in L infinity of this, Rn plus 1, which is taking values on the symmetric m plus 1 times m plus 1 matrices. Okay, such that the divergence of U is equal to 0. U is identically equal to 0 outside omega. In omega, U of Z belongs to some set K, okay? And you can think about the set K as describing exactly what this matrix U has to be. So what this matrix U has to be, so this matrix has to have 0 over here. And then there is a relation between this guy here, which is the trace-free part of this portion, because you see Q times the identity is of course not trace-free, but U is trace-free. So U is really the trace-free part of this matrix. And when I look at the trace-free part of this matrix, this trace-free part has to satisfy this identity. It has to be equal to V tensor V minus modulus of V squared divided by N times the identity, right? Where V is exactly this vector that I'm taking, so the first one. So let me just say U of Z has to belong to K for almost every Z in omega. Okay, and K is just the set of all matrices that satisfy the algebraic constraints. So definition, K is the set of all U's such that of all U's in understood as constant matrices, right? So the place where big U takes value. So such that say U m plus 1 is equal to 0. So this is what actually happens over here. And okay, these algebraic constraints are satisfied. Okay, so this is what we want to prove. And we will give two arguments. One argument will be sort of constructive. It will be similar to what La'szlo actually showed yesterday. That he was starting from this function identically equal to 0, and it was adding a lot of perturbations and slowly converging towards a function which has modulus of U equal to 1. So we will start from the matrix field which is identically equal to 0, which of course satisfies these two conditions but not this one. And then we will perturb it inside omega so that it becomes closer and closer to satisfy. Okay, so we will first prove. So we will first give a constructive argument. But then we will also see an abstract argument. So this will be more functional analytic argument. Okay. Yes. Sorry? What? Yes. Okay, it's important to distinguish two things. So maybe I should use two different lectures. One is the function U, and the other one is the space of possible values, which is this subset of the space of matrices. Okay? So the set K is the set of all U bar, which are matrix, which are symmetric, n plus 1 times n plus 1, such that U bar n plus 1 is equal to 0. It means this entry is equal to 0. And this algebraic condition is satisfied. So this algebraic condition is satisfied means you take this block, you take the trace-free part, and this has to be equal to V tensor V minus modulus of V squared divided by n. And you take this vector, and the modulus of that vector has to be equal to 1. So then I can look at my vector field. You know, this function has divergence of U equal to 0. U is identically equal to 0 outside K omega, and in omega, the value of U belongs to K in every point I'm actually going to take in time and space. Okay? Okay, so one thing which will be extremely important for us is the following observation. So I have this linear PDE, which is divergence of big U equal to 0. And so this is what is called Tartar's wave analysis. And what I ask myself is, what are the plane wave solutions of the linear PDE of this guy? So this is the question that I want to ask. So what are the plane wave solutions of the linear PDE? Divergence of u equal to 0. So what do I understand by plane wave solutions? So plane wave solutions are by definition the following. So they are solutions of the type u of z equal u bar times any function which is depending only on some particular direction. Okay? So this one is a plane wave solution. Okay, and lambda, so lambda is the u bar in the space of symmetric matrices with the property that there exists xi with modulus 1, or if you want, non-zero, such that u bar f of z dot xi is a plane wave solution for every function f that you can actually cook up. So this is a C infinity function of one single variable, right? Now, it looks like I have to take any function f, but because I can take essentially approximations, you can think about your good basis of function. Like, for instance, you can take any sines or cosines with whatever frequency you want. So it starts looking like a Fourier kind of analysis. Okay, and when you actually ask the question, so what is lambda now? So lambda any expression of this form is called plane wave solution. And lambda is the set of u bar for which for which there exists xi, such that no matter what you choose of f, it's always going to be a plane wave solution. Okay? Okay, it's actually a very simple computation. What is the divergence of something like u bar f of xi dot x? Okay, that's very simple to compute. So it's actually f prime of xi dot x u bar times xi. Okay? If this one has to be equal to 0, for every function that I choose, this one doesn't count, right? I mean, it's positive somehow. I can choose it positive wherever you want. And so what I want is that xi is actually in the kernel of u bar, okay? So lambda is actually equal to u bar such that the determinant of u bar is equal to 0. That easy, okay? And I want you to do the following exercise. So take 2 points in kappa. So take 2, say, u0 and u1 in kappa of the following form. So 1 is going to be v0 tensor v0 plus q0 times the identity, and then v0, v0, 0. So this is U0. And then there's another guy, which is going to be V1 tensor V1. But here I'm going to have the same. It's still Q0 identity. So this portion is the same. V1, V1, 0. So you might think about this as kind of the pressure part of your solution. So I'm just taking two states which have same pressure. Okay, then the determinant of U0 minus U1 is equal to 0. Okay, that is, the difference between the two allows a plane wave. So if I actually choose a sine function for my function f, I can find a solution which is oscillating between these two states, between the state U1 and the state U2. Of course, it's taking the value on the whole segment which is connecting them, right? But it's going back and forth between the two. And I can actually make them go back and forth very quickly. Okay, like, you know, like that. Okay, so, yes? Oh, yeah. Yes. Sorry. X is Z, yes. It's not, you know, I'm not telling you it has to be only an oscillation space-like. It can be space-time oscillation. Yeah. It's just a typo. Yes. Yes. Is a plane wave solution of this. Divergence of Z of U equals 0, yes. Only the linear part, yes. And that's what we computed, right? I mean, for this to be a solution, this one is equal to that. If I put this one equal to 0, it means that psi has to be in the kernel of U bar. Yes. Okay, so just keep in mind that this thing is telling you, anytime you give me two states in K, if the two states have the same kind of pressure part, which is this guy, I can actually connect it with a segment in lambda, okay? So for this reason, and we will discover, like, you know, maybe in half an hour why this is a sensible thing to do. So I'm not going to kind of discuss now why this is a sensible thing to do, because after I've done the proof, you will realize like, that is why he defined that object in this way, okay? I think it will become apparent later on. But anyway, let me define the following thing. So, U is going to be the convex hull of K times minus 1, 1. Okay, so sorry, let me, okay, done in this way is sort of, it's a little bit confusing, yes. Let me do the following. So let me define something like K0 is going to be, you know, like the one with 0 pressure. Okay, so K0 is the one with 0 pressure. Hopefully I'm not going to do this mistake. I've just realized I'm changing, while I'm actually giving the lecture, I'm changing the notation of the paper, which is not a good idea. But anyway, so sometimes I might forget this 0, hopefully. So now this is kind of the 0 pressure, so it's kind of like, you know, kind of cutting with putting this guy equal to 0. And now let me define U as the convex hull of K0 times minus 1, 1. Right? I'm thinking about this as a linear coordinate in the space of my kind of matrices, right? So I have like, you know, the slice which is trace 0 and the slice which is trace Q. It's actually, this one is actually the trace of the full matrix because I have the entry 0 over here actually, so, okay? So this is my U. And now I'm going to essentially give you what is the kind of statement for the constructive argument and the statement for the abstract argument. Okay? So the constructive argument will be something like the following proposition. Before I do that, so exercise. Easy. So this one is the easy exercise. So the convex hull of K0 has non-empty interior and contains the 0 in the interior. So has non-trivial, or let me put it this way maybe. So 0, the origin, is in the interior of U. So that's the easy exercise. And that's all we need. But if you want to be fancier, so this is the difficult exercise. And the difficult exercise is compute U. And by compute, I mean there's a formula, which is actually very elegant. So your set U is going to be satisfying certain inequalities. You can write down the inequalities and sort of completely characterize the set, okay? It's not done in my first paper with La'szlo, but it's done in the second paper with La'szlo. So you can actually compute it. It's a very nice formula. Okay, so now I can actually give you what is the constructive argument and what is the abstract argument. Okay, so the constructive argument is the following. Proposition. Okay. Now, I will switch back and forth between, writing my matrix as U, big U, but sometimes I really want to refer to kind of the components. So the vector component, the smaller trace-free matrix component, and the pressure component, okay? So I will start doing this over here. So there exists a sequence UK. So this is going to be, these are going to be the components. So these are all C infinity compactly supported in omega, satisfying divergence of UK is equal to 0, of course always in Z. UK takes values in U for every Z. Of course, for every Z in omega, but also for every Z outside, because 0 is in that convex hull. And then finally, UK converges to some U strongly in L1. And U, big U, now has the property that it's going to sit on my set K0 times minus 1, 1. For almost every Z. And that is the solution of Euler, which has compact support and which has modulus which is identically equal to 1 over there. And U0 equals 0. Now, okay, done in this way, it looks funky, right? I mean, like you give me any sequence which is doing this, and then I add 0 and I do it. But I mean, the upshot will be that there's going to be a recursive construction. So I will actually construct my map UK plus 1 from UK. So it's we are a mix in between So it's like a Markov process, right? So I don't care about what happened somehow before. You give me UK, and I'm able actually to produce UK plus 1. So there's an algorithm. Okay, so this is really algorithmic. No, no. The pressure is going to be between -1 and 1. I don't care. Not necessarily modulus equal to 1, right? It's on the whole segment. I'm really not caring about what the pressure does. You can actually keep track of what the pressure does. You can make things pressureless at a certain point. But I don't want to insist on that somehow, okay? But definitely you can do better than what I'm doing over here. Okay. Sorry? No, it's not going to be on the convex hull. It's really going to be on the extreme points. That will be the whole point. Because if it is on the extreme points, then it's a solution of Euler. If it is inside, it's not a solution of Euler. Okay? So you can think about if you're used to some other type of arguments, you can think about the PDE, which is taking values in here, as a relaxation of my actual PDE. And I'm just telling you, I start from 0, which is kind of the most relaxed state, and I start actually kind of deforming my kind of, relaxed solution in such a way that it becomes closer and closer to be a solution. And then in the limit, I will actually converge to the solution that I want. Okay, and now here, let me give you the abstract argument. So the abstract argument is, I think it's going to be surprising at least for some of you. So, okay, so take the following space. So take X is equal to the following. So it's like U, C infinity and compactly supported, solving divergence of U equal to 0, and solving U of Z belongs to U in omega. Okay, and compactly supported in omega. Okay, so this is kind of the sequence that you have over here. Okay, belongs to this X. And now close it in the topology of the weak star convergence in L infinity. Let me just write it this way. L infinity weak star. Okay, it's a bounded subset of L infinity, so it has a metric, okay? It's a metric space, because the L infinity weak star topology is metrizable. So X, D, so where D metrizes the weak star topology. So this is a complete metric space, right? It's actually even a compact metric space. Okay, now Y is going to be U in X. You see, because it's in X, the closure will satisfy this equation automatically, right? I mean, I don't need actually to specify that it satisfies this equation. And the value of the points in the closure is in the closure of U, right? Just by a very simple argument, because this guy is convex. So, but I'm just going to be looking at the U of X such that U of Z is in K0 times minus 1, 1. The solutions of Euler, right? I mean, as soon as I know that, they are solutions of Euler, with modulus of the velocity equal to 1. And the claim is the following. Y is a residual set in X. And you got it right. Y looks small to you, but it's not a meager set, it's a residual set. The ones who are not solutions are actually meager, right? Which looks somewhat crazy, huh? It's like I'm telling you that the boundary of something is prevalent in the something. Okay, you can think of it as a manifestation of the fact that there's some infinite dimensions, right? I mean, like, And again, there's a probability audience over here, so you're probably very well trained to understand that if I go with higher and higher dimension, actually what is close to the boundary of a ball is more and more prevalent compared to what is inside, right? And so when you actually take the limit, essentially everything is lying on the sphere, okay? There's some idea like that. But then, of course, once you have that, of course, this sequence exists, right? I mean, XD is a metric space which is non-empty. There's no doubt. There's zero inside. So because of the bare category theorem, Y is non-empty. It's actually big, it's huge. And we found our solutions, okay? So now, that looks really magic, but let me convince you it's not. So let me look at the toy problem, and the toy problem is the following. It's almost like the toy problem of La'szlo, but okay. The toy problem of La'szlo was too toy. So now, you know, our toy is kind of, you know, that was like really toy for babies. Now this is going to be a toy for bigger kids. Okay, so let me look at this other system of PDEs. So, toy problem. So the system of PDE is going to be curl of a vector field V is equal to 0, and modulus of V is equal to 1. Okay, it's a strange way of writing it, right? I mean, anybody in the right state of mind, this is the so-called iconal equation. So everybody in his right own state of mind would say like, okay, V locally is the gradient of a potential, and the PDE is modulus of gradient of phi equal to 1, right? So that is the so-called iconal equation. But why do I want to write it in this way? I want to write it in this way because you see a formal analogy with the other PDE, right? So I have a linear PDE, and I have a constraint over here, okay? So now, this is my linear PDE. Okay, this is the algebraic constraint. So kappa now is going to be defined as V bar in Rn such that modulus of V bar is equal to 1. Okay? And U is the convex hull of kappa. Well, the open set of the convex hull of kappa, sorry. I think I actually always forgot. So when I was writing actually U, I had in mind to be really in the interior. So it's always going to be kind of the interior of the convex hull, in fact. Sorry about that. So I want really the interior of the convex hull. And now what I'm looking for is, first of all, the constructive algorithm. So there exists a sequence. So you give me an omega fixed in Rn, bounded. So the constructive algorithm is actually telling me there exists a sequence Vk such that, okay, so these are C infinity compactly supported in omega. Vk belongs to U. Vk of Z belongs to U for every Z in omega. The curl of Vk is equal to 0. And Vk is converging strongly in L1. To V. Of course, then the curl of V is equal to 0. This is an outcome of the convergence. But what I really want is that modulus of V is equal to 1. Because modulus of V is equal to 1 means modulus of V belongs to K. Okay, V belongs to K in omega. Okay, and the constructive, sort of the abstract argument is going to be the same as there. So I'm not going to write all of these states. So construct the set X, which is the closure in L infinity weak star topology of this. Put the metric, look at the set Y, and then I'm going to just, you know, Y are the ones which actually take the values in K. And then I'm going to prove that Y is residual in K, in X, okay? So y residual in X. If you want, I'm giving you another exercise, which is formulate what X and Y are. Okay. So which proof do you want first? The constructive one or the abstract? Any preference? Anybody has any preference? Any vote? Abstract. Okay, excellent. Very good. Abstract. Okay, so first of all, there's a very interesting lemma. So take the identity map from X to X. Okay? But put the weak star topology over here and put the strong L1 topology over here. So it's, I mean, I'm deceiving you. It's not really the identity map because they have two different topologies, right? So yeah, it's the identity map, but for instance, it's not continuous because the topologies are different. Okay, so exercise. Identity is the pointwise limit of continuous functions, of continuous maps. And it's a simple exercise. So all you do is, instead of mapping V into V, map V into a mollification of V. Now, because you're mapping into a mollification, things are smooth. Oh, sorry, wait a second. So it's the other way around, sorry. Sorry? Yes, otherwise it would have been continuous. Yes, sorry, I'm being silly. So here you put the weak star topology, sorry, and here you put the strong topology. Yeah, I saw some of you were looking at me in a funny way. Yes, it's the other way around, that it's not continuous, right? I mean, if you're converging strongly, you're converging weakly, start, but if you're converging weakly, start, you're not. Yes. Okay, now it should be clear to you that this map is non-trivially continuous, right? I mean, because I'm mollifying, that's the mollification sort of transforms very vague convergences into stronger ones, okay? And of course, if I send the parameter epsilon to 0, I'm converging strongly in L1 to the single guy V, right? So it's pointwise convergence in the sense that if this one is my map I'd epsilon, right? So the pointwise convergence is that I'd epsilon of V is actually converging to V strongly in the topology of L1. Okay, and now here is the lemma that you need to know. This I'm not going to prove, but it's a very beautiful lemma in Baire category theory. So this is what is called the Baire 1 map, pointwise limit of continuous functions. So points of continuity of a Baire 1 map form a residual set. Okay, so points of continuity of a Baire 1 map. So this is just saying the identity is a Baire 1 map. So points of continuity of a Baire 1 map form a residual set. Okay? Very nice. So the claim is the following. So if V is a point of continuity of the identity, then modulus of V has to be equal to 1 almost everywhere on omega. So your V is in Y, okay? So the points in Y are more than the points of continuity of the identity. So because these ones are the subset. So this one is residual, that one is bigger, is residual too. Okay, so here's the proof. So your V, and this is very important, so your V, if you define X correctly, is in the closure. Oh, shit, I'm solving actually the exercise for you now. So V is in the closure of these guys. So V, which are C infinity and compactly supported on omega, divergence, curl of V is equal to 0. And V of Z belongs to U for almost every Z. Okay? So V is in the closure of that. So there exists a sequence Vk in the weak star closure. So there exists a sequence Vk which is converging weak star to V. But remember, V is a point of continuity of the identity. So if it is a point of continuity of the identity, every sequence which is converging weakly star had better converge strongly, right? So hence Vk is converging to V strongly. Okay, now V, you told me, unfortunately, it does not have modulus of V equal to 1 almost everywhere, right? So the set where, say, the modulus of V is below 1 minus epsilon must be at a certain point of positive measure, right? So there exists an epsilon and a delta bigger than 0 such that this set, it's an open set. So let me call it omega k. So this is the sets of points, so this is the points Z, such that modulus of Vk of Z is less than 1 minus epsilon. Okay? So this guy has measured at least delta. Okay? Very good. Now I want to actually make perturbations. So I want to perturb Vk to a new guy. Let me call it V tilde k. And what I want to do is I want to make this perturbation V tilde k in such a way that so from Vk, I want to produce V tilde k so that V tilde k is still converging weakly star to V. Okay? But the L1 norm of Vk minus V tilde k, I don't know, is bigger than delta divided by some constant. I mean, it's going to be a dimensional constant, but you know, it's a positive constant. And now I've reached a contradiction, right? I mean, because V tilde k is converging weakly to V, weakly star, but it's not anymore converging strongly if I have this. Okay? How do I do that? Assume for the moment that V is constant. Okay? So assume Vk is constant. So Vk is not really constant, right? But it's smooth. So it is approximately constant at very, 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 very small scales, okay? And so I can't really say that Vk is constant, but think about it. So this is maybe my omega k. Now, inside over here, I can cover with very small balls. And I can make things in such a way that in each of the ball, the value of Vk is almost constant. The balls are pairwise disjoint, and they cover at least a portion of omega, right? I mean, a geometric portion of omega, okay? So in each of these small balls, I will be approximately constant. Okay, now what do I want to do? Now I want to look at this ball over here, right? My vector on this ball is constantly pointing into some direction, which is shorter than 1 by epsilon, okay? Now I want to approximate weakly star with something which is kind of oscillating between, you know, like a longer vector, which has modulus 1, and its opposite, okay? So here I have somehow some, you know, let us think that I'm oscillating along this line, right? So I have a function which is constantly equal to somehow 1 minus epsilon, and I want to approximate it with kind of oscillations of this type, right? So here it's going to be 1, and then here it's going to be minus 1. And I want to keep the average actually constant. So here it's going to be 1 on a very large point, and then here is going to be minus 1, right? On this very small point. And then here 1, and then here minus 1. And then here 1, and then here minus 1. Now the distance between my, you know, the distance between my function and v is always going to be at least epsilon. So maybe I should have said that here I'm going to have delta times epsilon actually, okay? So there's always a certain distance, okay? And obviously, if I make the frequency of my perturbation very, very, very large, right? I'm just having many wiggles, many tiny oscillations. So I will be L infinity star very close to my initial decay. Okay, that's what I want to do. Now, this is if I only were to like have modulus of E equal 1. Oh, then I have to smooth it, right? So, okay, but I smooth it kind of this way. That's not a problem, okay? So now I would like to do this, but to be able to do this, of course, I still need to actually respect the divergence equal to 0. Not only I need to respect the divergence equal to 0, I have to make my kind of perturbation compactly supported over here. Sorry, not the divergence, the curve. So I have to make my perturbation compactly supported over here, okay? Without destroying that picture. Okay, so how do I do that? Okay, so remember that actually curl of V equal to 0 means that V is the gradient of some potential phi. Okay? So I have a function phi, and you know up to, so the gradient of the phi is almost constant. So it's going to be like a linear function which is growing this way. If I choose the coordinates correctly, I choose the coordinate in such a way that my function looks like this way. So the function is essentially growing over here. Okay, and then it's constant in the direction which are coming like out of the blackboard, right? So this is my function phi of z. Now I want to kind of perturb this function to a new function whose modulus of the gradient is equal to 1. What can I do? Well, I can do something like this, right? So here I have the slope equal to 1, and here I have the slope equal to minus 1. So slope 1 and slope minus 1, slope 1 and slope minus 1. So that is easy to do, okay? So if you think about it for a moment, it shouldn't be a surprise to you that this looks like this. So my perturbation, so let me call it phi tilde of z, looks like phi of z, and then I'm adding a highly oscillatory function. So something like you know, if kind of this one is lambda, right? Actually, if this one is 1 over lambda. So I'm adding a specific function, and this specific function is a function psi lambda times z. Okay, so this is kind of the basic oscillation that I'm adding on top of it. So all I'm saying over here is that if I take this function that I've drawn, of course I can smooth it. And I subtract the value, I just have a periodic function, right? And I'm just making the period larger and larger. Now, this is the potential, so what is going to be my function v? My function v tilde is going to be the gradient of this guy, right? So v tilde is going to be the gradient of this guy. Oh, wait a second. So you should even realize the following. So actually, the real thing which is happening is that I have a 1 over lambda over here, right? So if I increase the period, the function becomes shorter and shorter. Because actually are the values of the gradient which are constant. I mean, which are always the same, right? So I'm keeping the slope approximately equal to 1 and minus 1. So it's really the values of the gradient of this guy, which is going to be my v tilde, which I want to be the correct values, right? So closer and closer to 1. So when I compute the gradient, of course, this lambda goes away, right? Which is, so in other words, the function which is really periodic, which I'm adding, is not the function of the potential, it's not the potential, but it's the gradient. Right, this one is periodic. Okay, now you should realize something interesting. So, of course, I have different perturbation over here, right? I mean, I have some perturbation over here, some perturbation over there, some over here, some over there. There's no way they are going to agree, right? I mean, because in some direction I oscillate in this way, in some other direction I oscillate this way. So I need to cut off my perturbation. But what happens if I cut off? So if I cut off, it means I add the function chi over here. I mean, if I add a function chi, of course, this picture, so this guy has the correct modulus, but with the addition, I get an error term. But you see, the error term does not cancel the lambda over here, as it happened actually with the very fast oscillation. So I get gradient chi, psi, and then I have the 1 over lambda. So maybe here I need a cutoff which has very, very large gradients, but lambda is up to me to choose. So I choose a huge lambda, and I treat this as an error term. And then I got my perturbation. Okay, so this is the abstract argument. So how about the constructive argument? So the constructive argument just simply says the following. So do with what we just did iteratively, right? I mean, actually, for this one to be a valued approximation, you always have to stay with the modulus a little bit below, right? Because I'm telling you that you have to go into the interior. So in principle, I can start from 0. I start adding oscillations. And then I'm not happy. This is not sufficiently close to modulus 1. So I repeat that argument. And I repeat. And what I'm just going to tell you is that if you shoot the frequencies very, very fast to infinity, actually you're converging strongly. That's the constructive argument. How am I going to do that? Okay, so you get from Vk the new Vk plus 1. So, I mean, I gave you the algorithm. Notice something like this. Along the algorithm, I want something happening, which I can certainly arrange. I want something like, 1 minus modulus of Vk plus 1 in L1 norm is going to be less or equal than 1 minus a certain fraction, constant 0, times 1 minus the modulus of Vk. In other words, my distance to being actually modulus 1 is decreased by a constant factor each time. This is what I can arrange. I can certainly arrange that because I can cover, I don't know, a portion, maybe 1/1,000,000 of the whole omega k. And on that portion, I can actually decrease the error by, say, a half. So the error to have actually modulus 1 is always decreased by 1/2 millions. And maybe, you know, a million maybe is ingenuous. But the only point is that I just need something which is less than 1, because if I iterate this guy, of course I just get that this L1 norm is going to be less or equal than a constant times 1 minus C0 to the power k, right? And so if I can show you that I'm converging strongly in L1, the moduli will converge to 1, and so the modulus of the final function is actually equal to 1. So how do I actually get strong convergence? So this is interesting. So say that I am at step k. So at step k, now here, it's a simple argument, but each time I have to remember. At step k, so choose a mollifier okay, a mollifier. Okay, choose a mollifier, say phi eta j, eta k, with the property that the L2 norm of Vk minus this mollifier in L1 is less than 2 to the minus k. I can do that, right? I mean, it's a smooth function. I choose eta k sufficiently small. I have a mollifier which does that. Okay, now when I'm producing from Vk, I am actually producing Vk plus 1. Okay, when I'm producing Vk plus 1, I want to satisfy the following. So Vk minus Vk plus 1 mollified with, okay, I use rho. Okay, mollified with rho eta j in L2 is going to be less than 2 to the minus k for all the j less or equal than k. Again, I can do this, right? I mean, I actually can choose Vk plus 1 so that it is in L infinity weak as close as I want to Vk, okay? I have a finite family of mollifier. I have eta 1 up to eta k over here. So I have a finite family of parameters. So I have to accommodate for a finite number of inequalities, and I know that if I shoot the lambdas huge, right? I mean, the control on how weakly star close Vk plus 1 is to Vk is just given by those lambdas, right? So if I choose the parameters really huge, I'm so close that I will be able to accommodate that. Okay, so now my claim is that because of these conditions, because of the conditions, Vk actually converges strongly to V. Okay, and let me give you the argument because it's really cute. Okay, so first of all, so passing to a subsequence, I can assume V convergence. Okay, so Now look at this, right? So if I'm actually looking at, say, zk star rho eta k minus z star rho eta k, okay? So I can just say this is less or equal than the sum for j equals 0 to infinity, and then I'm going to have zeta, say, k plus j star rho eta k minus z k plus j plus 1 star rho eta k. So this one in L1 is going to be less or equal than 2 to the minus k plus 1. Yes? Oh, yeah, it's the same as V, sorry. Right, and then I sum all of this series, and I know that this is going to be less or equal than 2 to the minus k plus 1, because I'm summing a geometric series. Okay? And now, estimate actually, I don't need to pass to a subsequence, sorry. What you realize is actually that the estimate that I gave you, to the final V, yes, to the final V. So what you realize is that the estimate that I gave you actually tells you that this thing is a Cauchy sequence, right? So for every modification, I know that I am converging to something. And so that actually tells you that the whole sequence is weakly star converging, certainly to the same thing. Okay, so passing to a subsequence is actually not needed. So, okay. So I have that, and now I want to actually estimate Vk minus V in L1, right? So I can use the triangle inequality and say, okay, this is going to be less or equal than Vk star rho eta k minus V star rho eta k, right? And this I just discovered is less or equal than 2 to the minus k plus 1. Okay, then I have Vk star rho eta k minus Vk in L1, and this is 2 to the minus k. And then I have V minus V star rho eta k. And what is this? Well, I don't care. I keep it. Now, this is certainly converging to 0, because I am even quantitative. Here, I don't have any quantification, but you give me an L1 function, I modify it with something, it's converging to 0 too, right? So this one is converging to 0. And then I have strong convergence. Sorry? Oh, yeah, okay, I'm doing with the L1, sorry. It doesn't quite matter, right? Because the functions are all bounded actually by 1, so I can use any LP norm. So the only thing I can't do is I cannot use the uniform norm. Yeah. So I guess in the thing we use the L2. Okay, very well, this is the toy problem. Now, how am I actually going to arrange the real problem? Okay, see, in the real problem, I'm just claiming that, modulo that you actually get the right tools, the framework is there. So what are the right tools? What did we use? So first of all, we wanted to be able to perturb, right? We wanted to be able to perturb so that we are actually, if we are far away from our constraint, remember the constraint was modulus of k equal to 1. If we are far away from our constraint, we actually want to be able to perturb. What it means to be able to perturb? It means to be able to find a line segment in your interior of the convex hull, which is sufficiently large. compared, I mean, sufficiently large compared to what? Sufficiently large compared to the distance to the extreme points. Okay? So now, here in the circle, I was somewhat cheating because the circle has the following property. Every point in the interior of the circle is the convex combination of 2 points on the convex hull. Okay, so now we're not going to be in that favorable situation because, first of all, I tell you, we don't even need to compute the convex hull, okay? But secondly, even if we were able to compute, it sounds very unlikely that it's going to be that nice, right? So think about it. So my set K, for instance, if you remember, is the set of matrices. So say that we are, for instance, in 2 dimensions, right? So it's in a set of symmetric 3 by 3 matrices, right? Where the final guy is equal to 0 and the trace is equal to 0. So you make a dimension count and, you know, it's a 4-dimension set. But then what is your set K? Your set K is the matrices which have a certain particular form in which the form is actually parameterized by a vector with modulus 1. So in 2 dimensions is a 1-dimensional. It's a curve in R4. And I'm telling you the convex hull of this curve in R4 is a 4-dimensional convex set. There's no way that only convex combination of 2 points can actually achieve every point inside the convex hull, right? Because if that were 2, I have 2 parameters plus lambda, and so that can span at most a 3-dimensional set. Okay, so you are 1 dimension off. You go higher up, say you do this in 3 dimensions, 4 dimensions, and so on, it becomes actually less and less favorable. But I have something which is called Kara-Teodori argument, or Kara-Teodori theorem. Kara-Teodori theorem tells you, you are in a very high Euclidean space, and you look at the convex hull of some set. Every point is a convex combination of at most n plus 1 points on that convex set, okay? So if you are a convex combination of n plus 1 points, right? So you write down your point as this convex combination. Well, because you are, say, epsilon away from the set K, at least one of these guys have to be a somewhat large segment, okay? So there's going to be a large segment in which you can actually go and add a wave which is all inside your constraint, okay? So step 1, in the actual problem. So find a plane wave so here you have your set K. So here you have, say, your point which is far from the convex hull. Now, it's not really this way, the set K, right? I mean, because you have to think it's in very high dimension. So here it looks like the boundary of something, but it's not really that way. So here you are inside the convex hull, and you want to find a sufficiently large segment, right? In which you are in a direction where you can oscillate. So this is like as a direction in lambda. Okay, so use Kara-Teodori theorem to find this perturbation. Let me write down the precise proposition that you really want to prove. Okay, so the precise proposition that you really want to prove when everything becomes quantitative is the following. So oh, wait a second. So this is step 1. Okay, there is then a step 2. You want to cut it off. So cut it off, but keeping the linear PDE. So if you remember, how did we do that? Well, we did it by finding a potential over here, right? So we found a potential because the potential is somewhat an antiderivative of the perturbation that you added. The potential gains the 1 over lambda. Okay, and then apply to the potential the linear differential operator, which spits back the function you're interested in. Okay, so to cut this off, you need a potential. Okay, so the actual technical proposition that you can state, and which then makes somehow all the abstract machinery work, or this machinery work, if you want, I mean the precise perturbation in which you're constructing the sequence, is the following proposition. And I think you kind of believe me, and you can look at the details, that Kara-Teodori is going to get you out of the situation. But the potential looks like a pretty tricky thing, right, in principle, because, like, you know, I have to come up with something for a complicated linear PDE. So you remember, for instance, I have the divergence-free condition. Okay, fine. We know how to construct potentials for divergence-free vector fields, right? But it's a matrix, right? So if I start actually writing potentials for each of the row, who actually tells me that when I multiply by the cutoff, the matrix actually keeps being symmetric? That you don't know, okay? So you will need to be smarter than that. So let me give you the proposition for the perturbation. So this is the perturbation that I'm going to actually stick into each of these guys. And it says the following. So so this is the localized plane wave. And so this is the thing that you actually want to cut off. So say that you have an A, which is some V0, U0, Q0, and this is in lambda, right? So it's it's what you want to add. Okay, now this has V0 is different from 0, and sigma is the line segment joining A and minus A. Okay, what you want to do is something like this. So for every epsilon bigger than 0, you want to cut off somehow the plane wave which is oscillating in there. So for every epsilon bigger than 0, you want to find VUQ, so smooth solution of the linear PDE. And the linear PDE is actually this guy. Okay. With the following property. So the first thing you want is that the support of this VUQ is contained in the ball of radius 1. So you cut it off. Second, you want that the image of VUQ is in an epsilon neighborhood of your segment. Somehow in our toy problem, what really happens is, if I don't have to cut off, I'm really in the segment. If I have to cut off, I have a small error, and so I might fall outside of the segment. And then finally, the integral of modulus of V of xt dx dt, this is going to be bigger or equal than a geometric constant alpha times the modulus of V0, okay? So this will mean I'm oscillating in this segment, but, you know, my oscillation somehow is substantial in such a way that, you know, the total mass is bigger. And so you need to, so the only thing you actually need to do is you need to write down what is the perturbation that you want to add, maybe, you know, put sign, which is oscillating over this segment. So you put something like, okay, lambda has a direction psi, so your function VUQ at first approximation is going to be V0, U0, Q0, and then there is sine of a very high frequency, psi times Z, okay? And then you want to cut off this guy. So, sort of sketch of proof. So so VUQ is going to be something like V0, U0, Q0. Then you have something like sine of lambda psi dot x. So this psi is linked to the state V0, U0, Q0 in such a way that you're solving the equation. But then what you want to do is you actually want to write VUQ as some linear PDE, which I'm going to tell you, times some potential. And now this is going to be a second order operator. So actually the potential will get something like divided by lambda squared. Okay, so this is maybe going to be V tilde, U tilde, Q tilde. So this is the potential for, or actually, let me see. Yeah, actually in that, it's maybe VUQ, and then V tilde, U tilde, Q tilde is really what I want. Maybe. And so you're going to get the potential for VUQ. If I remember correctly, the potential is second order, so you're dividing by lambda square. And then here you multiply by the cutoff function chi. This is the cutoff. And when you compute what is the V tilde, U tilde, Q tilde, okay, so you get what you wanted. So when you actually apply the potential has the oscillation also. So this potential is some function P of lambda psi dot x. Maybe P is not a good name. I don't know, let me call it maybe big A. It's a tensor. So when I apply somehow two derivatives, this guy cancels, and so I really get VUQ times the cutoff. And then I have something which is order 1 over lambda, and maybe even something which is order of 1 over lambda squared, right? As in there. Okay, so let me show you the potential because it's cute. So here's the lemma that actually does the job. Okay. So lemma. So pick E, K, L, I, J. So these are tensors in C infinity of Rn plus 1. So these are 4 tensors. So they are functions with I, J, K, and L, which are equal to 1, and they go to n plus 1. Okay? So it's a 4 tensor, if you want. So, and you have the following property. So first of all, E is Q-symmetric. In IJ and KL. And this means that you have the following relation. So AEKLIJ is equal to minus ELKIJ is equal to minus AKLJI. Of course, is equal to ELKJI. Okay, then U equal to L of E, which is defined by the following relation. So it's 1/2 sum over K and L of D2 KL of E IL KJ plus EJL KI. Okay, so this guy is divergence free and symmetric. Okay, moreover, so this is kind of, because remember, we want somehow one entry of the matrix to be equal to 0. So moreover, if you actually have this equal to 0 for every I and j, then u m plus 1 is also equal to 0, okay? Which is what you want to accommodate. So now, there's one step. So I'm going to show you, this is a very easy computation. So both that it is symmetric and it is divergence free. So this is a very easy computation. One thing that you might wonder is, can you actually find that potential? And because this guy has some specific, formula, in particular, you can think about, like, you can act with transformations in such a way that, for instance, V0 is a certain particular preferred direction. You can actually find a potential by hands, essentially, for your plane wave, okay? But because it's a cute computation, let me show you why the divergence of u is equal to 0 and why u is symmetric. Okay, so this is uij. And you see, the symmetry is because if I change I and j, I'm getting j and I over here, and I'm getting I and j over there. So this sum actually makes it symmetric, right? So the symmetry is obvious. And now divergence free. So divergence free means I'm computing something like di uij. Okay, and then I have the sum, and here I have the sum over k and l, and I have three derivatives, so I, k, l, and then I have e, I, l, k, j, plus e, k, I, j, l. Okay, but you see, for instance, here I have I and l, right? The guy is symmetric, the derivative, but this guy is anti-symmetric. So that cancels. Here I have k and I, and that's exactly what I have over here too. I have k and I. So this guy is symmetric in k and I, this guy is anti-symmetric in k and I, and so it cancels. Okay? Now, just one final remark. So, because when I was giving this lecture, so a friend of mine told me, like, so how did you actually get that potential, right? Which is a pretty good question. So, what actually happened when we were studying this is La'szlo cooked up a miraculous potential for the 2x2, I mean, in the dimension n equal 2. And somehow essentially went by hand. So he first generated a potential for each vector, and then he started fooling around in such a way that, whatever gets is again symmetric. And then he passed this miraculous potential to me, and I was kind of looking at it and staring. And because you can think about a potential for the divergence if it's in 3 dimensions as the curl of something, right? But you can also think about it as the derivative of a matrix, right? I mean, the curl of something is actually some, matrix kind of component. Okay, so that's how we came up then. I came up with somehow the general formula in any dimension. So this is what happened to us. But there's a way to actually try to cook up this potential, which is simply going to the Fourier side, okay? So if you go to the Fourier side, if you make a Fourier transform, all of the multiplications, all of the derivatives become multiplication by psi, okay? And so you realize that you're looking at some kind of, geometric surface, which is defined by some equations. And what is actually the potential doing? Well, the potential is essentially trying to parameterize, the points on this algebraic surface. And so then you can try to come up with somehow some explicit parameterization, which is the way you actually come up with those potentials. But okay, so that said, I'm 3 minutes extra time. I think it's better to stop. Alpha is time-dimensional constant. Yes, yes, it will depend on n. It depends on the volume of the ball, yes, and it might depend a little bit on the geometry of this set K. Maybe not. Maybe it depends only on the volume of the ball. Yep. Yes. Well, actually, the fact that I have a symmetric matrix is more kind of disturbing me than anything else. If I only had to have a divergence-free matrix, I would just simply take a vector potential for each of the rows. And then I wouldn't care, right? I mean, the only point I'm somehow kind of disturbed is the following. So I could try to do the following. I could try to take as a potential the vector potential for all of the rows. And then I just take, the curl of that. Okay, now what I'm afraid of is that it's just a coincidence that what you got was a symmetric matrix. When I multiply by the cutoff, that coincidence sort of disappears. And so it was a symmetric divergence-free matrix before I cut it off, but when I cut it off, it's not anymore. And so the fact that I have actually the symmetry relations to satisfy is more of a problem for me than an advantage. Otherwise, if I had only the divergence-free condition to satisfy, then I would simply take the vector potentials row-wise in 3 dimensions, for instance. In higher dimension, I would take, whatever the potentials are, which are sort of anti-symmetric matrices anyway. Okay, I guess there are no other questions.